Hi everyone. My name is Emmanuel Ko. I'm chairing the I think the last session for the conference, session 9 on AI and machine learning. I'm an assistant professor at the Singapore University of Technology and Design. I'm very happy to be able to chair this session, something that I'm also very interested in. Given the time that we have, which is really short, in fact, we started quite late, 3 minutes late. The idea is that so we have 13 papers. We have to finish it in 45 minutes. For those who have just joined us, if you have questions, please pose it in the Q&A chat box. And the panelists, ideally, if you could, please enable your video so everyone could see you. The format would be like this. Every author would have 3 minutes to present, so that we could finish in 45 minutes clearly. So 1.5 minutes introduction, and also the introduction of the paper, and then hopefully 1.5 minutes for the Q&A. And then I actually have the schedule, but yeah. So maybe a quick summary, just give it an overall picture in 1 minute. There are 13 papers, and you would see a variety of deep learning models being used. We see generative or discriminative usage of the deep learning models. Some authors had used pre-trained or even using APIs or training from scratch. The VGG19 is one of those that has been used by quite a few authors. Some of our popular models are Pix2Pix, GANs. Typically for style transfer, you see quite a few papers talk about style transfer. Even detection or segmentation, like a few papers looked at PointNet, UNet, and even using Pix2Pix for a discriminative usage. Also, you see a few clustering projects that use PCA, DSNY, as well as, of course, a mix of convolutional neural networks, fully connected neural networks, and even one project looked at the LSTM, which is the recurrent neural networks. A variety of architectural representation are used in the various papers. Most typically the 2D floor plans, 2D urban plans, and 2D sections, which then a few of the authors use these 2D representations to generate 3D architecture models. Of course, there are also some that looked at 2D photos of interiors for branding, for instance, using Pinterest, or for museums interior that used Instagram datasets. With a mix of 360 photos of interiors as well. There are also one of the project really interesting, looked at this sensor to kind of understand how one might behave in a toilet, in a cubicle, in a toilet, quite funny presentation. And some looked at 3D point clouds, as well as a few that looked at the ways in which one could visualize high dimensional data by doing dimensional reduction. So without further ado, I'll ask the first author, Hao Zhen. So what I'll do is that I will share my screen where you could see both the papers and also the schedule, 3 minutes. So Hao Zhen?
I'm here.
Yeah.
Thank you, Cole. So I'm Hao Zhen. I'm currently a PhD student in the University of Pennsylvania. So I actually have, so our team actually have 4 papers in this section. This is my first paper. So in our first paper, we use generative adversarial network, which is an image-to-image based neural network to learn the generation of architecture plans. So actually, the goal of this project is to teach the machine to learn how to generate architecture, especially the apartment floor plan, from the design boundary of this plan. So we use 2 data sets. One is our connected data set of Chinese apartment floor floor plan, and the other one is Japanese apartment floor plan, which contains like 1,000 or more architecture plans. Then we build two machine learning models. Then we compare the result as well as we test different boundary. For example, so we use the boundary from the Chinese apartment floor plan to test the model from the Japanese model. So then we conclude that the two models perform differently, and the design rules in Chinese plan is simpler than that in the Japanese plan. So the Chinese model performs better, and it can be used to generate the architecture plan in a very early stage. So this is our first paper. Yeah.
Okay. Thanks. That's amazing. Okay, it's really fast and brief and
So I try
concise.
to keep it very short.
Okay. Are there any questions from anyone, even the panelists, perhaps?
So maybe I just quickly introduce our other papers. So the difference between this paper and other paper is that this one it focuses on the apartment floor plan. In next paper we have one paper using the same model, but for the generation of city plans, which is related to urban planning. For the other paper, we use different models. So we use ANN-based, so it's vector-based model to generate the apartment floor plan, but we regard it not for the image, but for the vector-based data sets. So this is the difference between our three papers.
Can I ask you one thing?
Go on.
Yeah. Could you tell me like a kind of like your research novelty compared to others' works? Because nowadays many people use like a pix-to-pix to generate a plan or sections, whatever. So could you accentuate your like a novelty?
Yeah, you might know our previous paper in Acadia in 2018. We used a similar method to generate architecture plan, but we use the color coded for the plan first. Then we try to teach the machine to generate the drawing based on the color coding. So in this one, we try to teach the machine a harder job, which should generate the whole plan drawing only based on the design boundary. So we don't have any information of the segmentation of the plan. So this is the harder job for the machine learning. Then we also use two data sets, which comes from the Chinese one for plan and the Japanese one. So we want to compare the difference between those two by generating this kind of different models to compare the design of the two countries. So this is the novelty of this paper.
Thank you.
Yeah.
Yes, there is some question from the audience. The one asked about whether the data sets are open sourced.
Yeah, the first data set is published based on our first paper in 2018. I think it's not open source since I've done the cluster without reach a conclusion for that. Then the second data set for the Japanese apartment floor plan is open source. So I cite this data set from another paper. It's from a computer science paper. You can read from my references and find the paper. Then they have like link to download the data set. Yeah.
Okay. Thanks, Hao Chen. I think we'll see you later on in the other papers. Next, okay, we have, sure. Thanks, Kaita Kado on, I think they are using the PointNet. Very interesting paper.
Hello everyone, I'm here. I'm Keita Kado from Chiba University in Japan. My theme is about process path derivation method of multi-cell processing machines using deep learning-based 3D shape recognition. Yeah, we focus on possibility of multi-axis machine and continuous studies for applying the machines to part processing in architecture fields. So we summarize workflow for applying these machines to process the parts in two workflows shown in figure 1 or 2 in page 612. And So we employ developed generic CAM for applying processing paths for wooden parts. So how we can derive processing paths efficiently in separated CAM-based workflow is the goal of this study. So in this presentation, we propose a 3D shape recognition techniques for auto processing path derivation, specifically which joint type is this, or which processing pattern is suitable for each polygons. Sorry. So, we developed two types of model to 3D shape recognitions. So we attempt to employ a point net-based 3D shape recognition that classifies a joint type and segment process pattern in order to streamline the process path derivation in the separated CAM workflow. So the first step to exercise joint a Boolean operation between a 3D shape, 3D geometry over target component and its bounding box. The second step is convert the exact joints into point clouds. The third step is recognition and estimation steps. So the entire point cloud is classified into several types of joint types of a classification model, and each point is segmented into several types of several process patterns by segmentation model. The point-wise segmented results are bolted to determine process path of each pattern. So our study case is shown in figure 7, and the test case A is a typical component of the frame which has a flat tenon, open mortise, and open mortise. Each joint was properly defined, properly classified and segmented. And case B is a component of a reciprocal ball with convex corner joint on both ends, and each joint was properly classified and segmented. Case B is a component of reciprocal tower with a scuff joint on both ends, and each joint was properly classified and segmentation. In discussion sections, we discussed, we thought the segmentation got versatility for recognizing processing parts, but unfortunately, the model does not seem to work for trend joint types. So, future work is how we can prepare trend test sets that works for actual joints. So we think there are two solutions. The first is updating a test set using actual input seems to be still method. The second is a pre-process for removing drawing holes. So because the drawing holes seems to increase variations and make programs difficult. So at conclusion, the methodology was tested using 11 joint types and 5 process patterns, and both models performed over 98% accuracy for the tested test sets. The study cases showed that the proposed method has practical applications. And the importance of the data generation method fitting actual publication was highlighted in this discussion. That's all. Thank you.
All right, thanks, Kaita. Actually, I have a question. In the paper, you showed mainly digital models where you feed in as the test. Have you actually tried physical inputs?
Yeah, that is my future work.
Okay.
Yeah, yes.
But would it be radically more difficult or?
Yeah, actually, drawing a hole is make difficult to creating test training data. So we now development process for remove drawing holes and to address actual inputs for fabrications.
I see. Thanks. I think there isn't any question from the audience. So then we we have to move on. Thanks, Kaita.
Thank you.
Next will be Hao Zhen on the third paper.
Okay, so this is our second paper with my wife. So my wife was the first author. So here is currently a master student in UCL. So this is more related to the design domain. So in this paper, we kind of use the machine learning Vectorized 19 model as the base model. Then we use style transfer algorithm. So I think everyone knows style transfer is a 2D method, 2D machine learning based method to transfer style of image into another. So in this paper, we try to develop a new method of the 3D style transfer, which maps the style from an image to a 3D model. So the difference between the 2D and 3D method is that we regard the 3D model as 2D sliced plan of the model. Then we transfer the model into a set of plan, which is black and white image, and the black means the interior and the white means the exterior. Then we use this set of, for example, 200 parent section as the content image. Then we use the style image as a style. Then we use the traditional 2D style transfer to transfer the style from the style image to the 2D parent of the content image. Then we use algorithm to transform the 2D pixel into voxel. Then we stack them together to become a 3D model, a new 3D model with the style from the style image. So this is the this is more like the design related paper. Finally, we also use 3 different smoothing algorithms to rebuild the voxel based model into different curvatures or surfaces. Yeah. Finally, we use the dome as the, I think, what's the name of the dome? Yeah, so we use the dome as the base model, and then we see what's the result of the style transfer for the 3D model. Yeah.
Okay, thanks, Hao Zhen. Any question from anyone? Oh, okay, there's some question maybe. No, those were the old questions, sorry. The one question that I have actually is, it's interesting how you get the 2D pixels and then you voxelize them, but eventually it seems like you're not too concerned with the interior spatial configuration of the, in this case, the spire. Yeah, from the section.
Oh, yeah.
Is that something that is not of concern because you chose the rose window as a transfer style?
Yes. So we use the rose window as a transfer as a style image. Then I think you might know some other style transfer, 3D style transfer papers, which related to the surface or the facade of the model, or it's related to the rendering of the model. So there are 2 other machine model which renders, so which transfer the style for the rendering. Then they reconstruct the 3D model based on the rendering from different aspects. And also they use the another one. I think they use similar model to deal with the surface of the model. Then they create a concave surface based on the ground model. In our method is a fully 3D voxel based method, which regards the interior model as the voxel based model, which in which we can create the concave structure not only in the surface but also in the interior of the model. So I think this is the difference between our method and other 3D style transfer method. I don't know whether I answered the question.
Yeah, kind of. There are a few. Okay, one more question. How do you evaluate the efficiency of the model?
Here, since it's more like a design problem, so we don't actually evaluate the efficiency. For example, the time cost for the model. And finally, our goal is to generate a result. Is not to generate a result in a very fast way or in a very create all in a very efficient way. So we don't evaluate the efficiency, but we evaluate the final result, the effect or the modeling of the final result.
Yeah, in fact, some other papers from Hao Chen, he actually showed the loss and the accuracy, and that probably is more relevant for those papers. Yeah, I think we have to move on to the next paper, which is the Tisney. Oh, it's called Tisney. The paper is called Tisney. I suppose Hang will be presenting. No. So would Leo?
Yeah.
Ah, okay. Right. Sorry.
Hi everyone. My name is Leo. I'm Hank's student. So today I'm presenting. Let me try to request control somewhere. Sorry, can I request control, or you'll be just scrolling down? That's all right. So I'm presenting the industrial-based research paper on the Tisney dimensionality reduction tool for design data visualization. So nowadays, I think one thing we need to point out is in the real-world design practice, not all the data are equilibrium. It's not necessarily based on pixels or voxels. Sometimes it's embedded or relational in your design. And we use a lot data dashboard to visualize the process for design decision makings. And this is an example we take from HDR Inc. The idea is, what if the data shape is actually non-equilibrium? How do we make decisions based on this? And we use Tisney as a way to reduce the dimensionality of each data point. In this case, is the room data to 2 or 3 dimensions, and observe how they cluster to assist the design decision-making process. And I used we used 2 projects to, in fact 3, but due to the limitation of the length of the paper, we reduced to 2 projects. The first one was, and this is how we collect the data for the first project, basically using ISOVist. And this is inside of the orange graphic interface, how the data is processed and also made into a Tisney visualization as well. And move forward, I can show the project 1 is basically trained based on the data collected using room ISOVist and being clustered. As you can see, there are a few quite clear clusters indicating some rooms has similar geometric features versus other rooms have distinctly different geometrical features. I believe many scholars have studied the same thing using different convolutional neural networks, and I wouldn't spend too long on this. And the next example is just purely throw a ton of different room data into Tisney and let it cluster. And we can see that Tisney respects each feature of the data. We cluster the, we color this data into different by different features, and it shows consistently being clustered fairly well. It's actually the next graph. Thanks, Emmanuel. Scrolling further down. Yep. And here we go. So it is attempt to further integrate machine learning with the actual real-world design practice, and this is the result. In the future, I'm trying to study how we can represent and learn the relational data using graph neural networks, which brought to further discussion. Thank you.
All right, thanks. Thanks for your presentation. Very beautiful visualization, I would say. Any question from the audience? I'm curious, it's more like it's not a very important question, but is there any reason that you have chosen to use Orange 3 in this particular case?
Sorry, chosen what?
The Orange programming tool language?
It's a visual programming. Well, it has a Python library, but it's also a visual programming tool as well. So it's easier for beginners, say. And also, yeah, there are other tools as well, but I find Orange is probably in terms of the performance is slightly better. So I chose to take that.
Okay, Thanks. Very useful for beginners who want to play with Disney, I think.
Yes.
Next, we would thank you, Liu. We move on to the next, which happens to be my paper. So I'll do it really quickly because we're running out of time. So, so the focus, in fact, this research is called Augmented Museum. The research was done 2 years ago in Switzerland before I moved back to Singapore. The focus is on the investigation of how deep learning might potentially be used to reconfigure user experience, and in this case, in the context of museums. So in the paper, I showed 4 possible approaches out of the many infinite ones. But the emphasis is not so much about the specific construction of the neural networks. In this case, a few projects use APIs from the Microsoft Azure as well as the Clarify, where it's easy to get outputs without having training anything too seriously. So maybe one of the project, I would just highlight one of them. You could look at the other ones. So like in one project called reversibility, which is basically looking at how paintings may look at you as the visitor. So you could score the emotional tendency of a painting. And therefore, when you reconfigure, in this case, a slider in a web app, you could reconfigure the itinerary based on the emotional trend. Yes, so these are in fact the analysis of different paintings. These are the names of the paintings, where you could see that you could actually visualize yourself and the paintings in the same PCA or even Disney, in fact, to see the relationship of emotional response. The other project looks at Face++, which is allow one to do deepfake, but the question is I think at a high level is to question how deepfake might potentially be used to augment museum experience in a perhaps irreverent way, but I think it's still worth considering. Yep. So if you have questions, you could ask me. If not, I could also move on to keep to the time. Okay. Let's move on to the next person, Chen Yusheng San. Sorry, very sorry. You gave me this last minute this thing, no? So I could show it also.
Oh yes, thank you. Can you hear me?
It's a bit soft. Could you like yeah, up the volume?
I'm sorry, the internet and the connect is weak.
Yeah, go on.
Okay. Hello, everyone. Today, I'd like to share with you the topic of a rapid building density survey method based on improved UNet. We are a research team from the College of Architecture and Urban Planning, Tongji University, Shanghai, China. The main purpose of this research is rapidly extract the building area, building footprint, and building density over a wide range by using the open source satellite images. We mainly use deep neural network to implement this algorithm. To use a deep neural network, this method can be roughly divided into 4 steps: dataset preparing, model training, model evaluating, and the model application. Firstly, we downloaded the satellite images from Google Earth, manually labeled the footprint and split and resize these image pairs, and finally divided them into 3 data sets: training set, validation set, and the test set. Secondly, we applied the adapted UNet. We improved the loss function compared with the basic UNet with the loss function of binary cross entropy, and our improved loss function combines BCE and EOA. And the results showed that our improved UNet performed better than the vanilla UNet on our test dataset and the additional dataset. Thirdly, evaluate the model we trained. The dataset we used for training was in Suzhou, an important industrial city of China, where the terrain is plain we took the satellite images of Shanghai with the similar architecture, form, and terrain as the test set, and the results were pretty good, and the relative error of building density prediction is less than 5%. We also used the additional test set in Chongqing and Gulangyu, where the topography and the building arrangement was completely different from the training set. The results showed that our model still has high accuracy. For example, the relative error of building density prediction in Chongqing is less than 10%. At last, the model was applied to the building density prediction of Yangpu District, Shanghai. The total error is about 60 square kilometers. It takes less than 1 minute to predict building density on computer equipment with the NVIDIA RTX Titan graphic card. The density map extracted by our model in the good agreement with the actual situation. Okay, that's all. Thank you.
Thanks for the presentation. I think since we're running quite late, I think it might be good for everyone to present just to ensure that I would not miss out anyone, and then the remaining of the time we can then discuss. Yeah. So we move on to the next one. There would be is it Hao Zhen? No, Jin Mo, he. No, actually it's wrong. Hang Zhang is.
Yeah, it's me.
Hang Zhang, please. Yes.
Can you hear me?
Yep.
Yeah, all right. So my name is Han. I'm from the University of Pennsylvania. So let me briefly introduce my recent work, that is the three-dimensional architectural form style transfer through machine learning. So basically, this paper is trying to make the three-dimensional style transfer through the traditional, or let's say the famous style transfer algorithm, that is the cyclogram, the pixel-to-pixel, and neural style transfer. Basically, we got like two different methods of the slicing method. That is how to convert the three-dimensional model information into the 2D images. And that is the first one is the zero stacks. It's like slicing a cake from one direction to slice the whole model into dozens of the 2D images. And the second one is that we try to circle the whole model around and make the multi-view data set. And while we prepared our data set, we're trying to make the style transfer through the two-dimensional, and then we compile them to the 3D. And while we do this, we also add one step, and that is we try to apply a video style transfer into this three-dimensional form finding, and then this method will help us to maintain the continuity between each of the layers. And the next page is going to be the results of our style transfer. Maybe you should slide down to show the results here. Yeah, not this page. Yeah, here. So we got like the input and output are all the three-dimensional model. So our left one is the content model, and the right one is the style model. So we're selecting them and try to train them based on the cyclogram and the pixel-to-pixel. So pixel-to-pixel use the paired data set, and the cyclogram use the unpaired one. And the images below are the results with the cyclogram and the pixel-to-pixel. And we also got quite more results that is to use, or you cannot use the video style transfer. That is try to contain or not to maintain the continuity between each of the frames. And while we use the cyclogram and the pixel-to-pixel to do the style transfer, we also try to do the, so this is the multiple axis steps. And that is the previous training is like we try to apply the style transfer from simply one direction. And this step, we try to merge them together with the two or multiple directions. And that is the first going to be from the front to the rear, and the second going to be from the right to left. And then we try to combine them together to merge into a new three-dimensional form. Yeah. And also we also got results from the neural style transfer. Yeah, that's it. So this is like, well, during this training, we only got one style images, but we got one three-dimensional input model, and then we try to use the neural style transfer to influence each of the layers within the input model, and then try to recompile into a new three-dimensional form. And this is the result from the multiple view. And that is, we try to circle the whole model around and to apply the style transfer on each of the frames and then recompile them together to be a brand new three-dimensional model. So the next page is going to be like, we also use a color tag system. So that is, we try to color tag each different elements within the architectural general form, and then try to do the style transfer through the multi-view dataset. And this result is quite good.
Yes.
That's it.
Okay, thanks. Very interesting project. I think we can talk a lot more about this. So the next paper will be Jing Mo.
Yes, can you hear me?
Yeah.
Okay, let me start. Okay, hello everyone, I'm Jim Murray from Code Lab in Carnegie Mellon University. This research reports on a method for generating a building mass using deep learning techniques based on contextual geometry in urban context. First of all, we train a deep learning model to generate a quadrilateral as an abstracted footprint based on the neighboring morphological features. Then you can go down. Then we can reconstruct the building footprints in two ways. Can you go down? I mean, you can just, yeah, scroll down. 2 ways, I mean, a little bit more. So, and then, so our model generate a, predict a quadrilateral like a shape, and then we input a reconstruction of the predicted building footprint to the Messiner, which is a genetic algorithm based like a machine mathing automation tool for housing to generate an archetype of morphing shape. This research successfully illustrated how generative systems can extrapolate the dependency of the computational synthesis on internal building factors such as spatial adjacency, opening location, heat radiation optimization to incorporate external qualities that are barely captured with the metrics and requirements. And then also this research supports the generalization of the knowledge acquired from the data to novel cases with a function approximator. Our model learns a complex function that maps the relation between a certain notion of like a context and the desired footprint based on a data set. So yeah, that's all. Thank you.
Thanks. Interesting. Actually, I have some questions, but I can't ask now, just to be fair to everyone. Yes, so move on to the, I think, Hao Zhen on the urban filling.
My internet seems not so good, but this is our third paper. The methodology is similar to our first paper to generate architectural plan, but in this paper we use urban plan, which is color coded as our training data. So the input data is the urban plan with its road, river, green land system without the building. Then the output image shows the configuration of the building as the white pixels. So in this way, we have connected the data set from 8 cities from China, which represent the first, second, third, and fourth tier of the cities in China. Then we train the 8 different models for generating the urban planning of architecture based on its configuration of the road, river, and green system. Then we compare the eight model by actually testing them with different input settings by different model, and we have found that the generative results show some relation between the design rules of the cities in China. For example, the first or second tier city, they have similar design rules, and the third and fourth tier city have similar design rules, but they are different from the first and the second tile. But eventually, this model could be used for the machine learning to generate the urban planning at the very early design stage to help the urban designer or the architecture designer to plan their architecture layout in a very quick way. So this is our third paper.
Yes, thanks. I think there are interesting overlaps between your work and Jingmo. In that sense, where you consider the context, of course, the scope is a bit different. Let's move on to the next paper, which is Yunjing Han on branding.
Yeah, hello. Hello, my name is Yujin Han. I'm a PhD student at Yonsei University in South Korea. I'm going to briefly present my study, and the title is a deep learning approach for brand store image and positioning. The aim of this study is basically to find a new possibility for measuring brand identity, brand image, and brand positioning with the help of AI. So the research background is that consistent brand image and unique positioning are very important in the context of brand environments and brand architecture, but they are highly subjective and hard to be measured traditionally. So we were wondering, how can we improve the way of evaluating and analyzing brand identity, and looking for a new way of creating brand positioning map to help designers. So in this research, we firstly focus on whether deep learning could recognize brand identity in store interior design and classify the brand or not. So using pre-trained CNN model, Inception V3, which show high accuracy in image classification, we retrained with our own data. And the results shows that the brand identity and brand positions in the store interior images can be recognized. And in the second section, with this model, we made a brand positioning map using an image sharing platform, Pinterest. So with this platform, we prepare the input image data for each dimensions of positioning map, which reflect users' opinions and perceptions to branded store that is really critical to positioning map. So this study used this deep learning technology as an extension tool for evaluating brand identity. And we think this approach can be one of the methods to help designers to decision making. Thank you.
Thanks, very interesting also. Next, we move on to Baptiste Hicks.
Yep, so you may have seen the title and you may think it's a bit funny to start studying stuff to do with toilets and bathrooms. But really that was one of the driving forces for why we wanted to study this, is because there wasn't actually all that much research on how people use bathrooms and how they're designed. And so really the question that we wanted to try and answer was what behaviors can be detected in bathrooms using a variety of different models. And so really, this was a question of how we can implement machine learning technologies with sensors into private spaces so that we can understand them better. So not just really bathrooms, but this is like the first example for potentially work that could go into places such as army bases and hospitals, so on. And so we used an 8x8 infrared sensor, and we prototyped up a sensor and got a whole bunch of data from participants. And then we used a variety of different models, including Convel STM models, and just a bunch of different models. And we basically found that it was actually quite capable of differentiating between different behaviors in the bathroom. And we're hoping that this sort of technology would be able to enable people to be able to study bathrooms and other private spaces more effectively. Thank you.
Thanks, thanks, Baptiste. His video is very funny. You guys should watch it. Next, we will have Houghton on the vectorized drawings.
Yeah. So me again. So this paper is our last paper, and it talks about the same topic for our first paper to generate architecture plan drawings. But in this paper, we use a vector-based neural network, which is artificial neural network with customized activation function as well as the loss function instead of the image-based neural network. So we firstly have some testing experiments to teach the machining to teach a machine model to generate very simple geometries based on the vectorized data. Then we move to the generation of the architecture plans, in which we transform the image-based data into vector representation of the coordinates of each design element in the plan. Then we build our own neural network with sigmoid loss function as well as the mean square error loss function to evaluate this neural network. Then the final goal is to input the boundary of a bedroom and the position of the door and window, and then ask the machine to generate the position of the TV set, the bed, and the bed stand. So finally, we use this vector-based neural network to successfully generate different results. And we compare those results with the ground truth data. We found that actually the result performs better understanding and better results comparing with the ground truth. Also, we have a comparison between the vector-based neural network and the image-based. So in image-based, it will generate some kind of noise pixels, but in vector-based, we could revise, modify the boundary of this geometry, which makes a very clear prediction rather than image-based neural network. So this is our last paper.
Okay, thanks, Hao-Chen. Interesting use of the very simple, fully connected neural networks and yet yielding really interesting results. Last, we have Da-Yu Chu, the last paper.
Yeah. Can you hear me?
Yeah.
Hello, I'm Tam-Ki Cho, enrolled in the master's program at Department of Interior Architecture and Built Environment in Yonsei University. I'm working on recognizing architectural objects in floor plans using deep learning algorithms and applying them to building information modeling. And I referred the study to Hao-Chen's Acadia paper in 2018, and I learned a lot. Thank you. Existing floor plans represent much of the cumulative information about the overall building process, but it's too hard for the computer to directly interpret them as human does. So my research focuses to change the style of existing floor plans to an integrative format for the computer to understand the floor plans as humans does and make it a computer-readable medium using pix-to-pix. The data I used is the typical apartment floor plans in Korea, which has different LODs and scales, and there are some of my research results. This paper was used as the basis for my research, and in my ongoing work, I'm trying to use these images for modeling BIM models using the Revit API to utilize them in my domain, interior architecture, and many other BIM-related applications, such as circulation, design reference, and etc. So that's a brief introduction to my research, and thank you everyone for sharing time with me.
Okay, thanks, Da-Yu. Very unexpected use of the pix-to-pix for such object detection context. Very interesting. The thing is, we can't actually continue the session because we're like 6 minutes overrun. So please email the respective authors if you're interested to find out more. Yeah. Thanks, thanks everyone. We actually have to end now. We're 6 minutes late. Bye. Yeah. Bye everyone.
Thank you. Bye.
Yeah. Sorry, we just have to keep to the time. Really, very unfortunate. The tech support. Tech support. Are you? Could you close the session?
Oh yes. Thank you. Thank you, everybody.
Thanks everyone. Yeah. So sorry, we should have like at least 1 more hour to just discuss so many interesting stuff.
you.